Hello, my dear students. Today I am going to discuss crystal field theory of coordination complex. In the previous class, we understood valence bond theory. There we applied the postulates of valence bond theory to octahedral and tetrahedral complexes. And the valence bond theory suffered from some of the limitations. It do not explain spectral magnetic properties and it fails to explain the strength of the ligands. In order to overcome the limitations of the valence bond theory, soon after the valence bond theory, the crystal field theory is proposed. Let us look at the important postulates of this theory, crystal field theory. As the name indicates, crystal field theory. First time this crystal field theory is applied for the crystalline compound. That's why it is named as crystal field theory. The first important postulates of this theory is, this theory consider the ionic approach between central metal ion and ligand. According to this theory, the ligand and metal ion act as a point charges. As a result, there is an electrostatic interaction which is present between ligand and metal ion. That means, according to crystal field theory, the bond between central metal ion and ligand is purely ionic. And second important postulate theory is, when the ligand approaches the central metal atom, repulsion takes place during the interface of two atomic orbitals, and this repulsion leads to splitting of d orbital. So dear, you just look at here. According to this theory, ligand is possessing negative charge, electron rich, and metal is positive in nature, and between these, so there is a interaction. This is called as electrostatic force of interaction, or this is an ionic interaction according to theory of first postulates. And the second postulate is, when ligand approaching metal ion, in metal ion also valence electrons are present, and in ligand also valence electrons are present. When these approaching comes near to the metal ion, so there is a repulsion takes place. So this repulsion is responsible for splitting of d orbital, because you know that the d block elements are, it is one of the characteristic property that they are going to form coordination complex. So this d orbital, the valence d orbital, so split into 2d orbital, that is splitting of d. This is a new phenomena, dear students. I explained in detail in the next slide. So now you just listen it. So repulsion takes place, and this repulsion leads to splitting of d orbital into two, that is T2g and Eg orbital. So you just look at here, when ligand approaching central metal atom, so before all the d orbitals, these are the d orbitals of central metal atom, they are in equal energy. The 5 orbital possessing equal energy, these are called as degenerated orbital. Remember, degenerated orbital, that is the set of orbital possessing similar energy. These orbitals are called as degenerated orbitals. Before approaching the ligand, all the 5 orbitals are in equal energy state or degenerated. But when ligands approach the central metal atom, due to repulsion between the valence electron, so these d orbital split into 2 set of orbital. The one is called as T2g orbitals, and second one is called as Eg. T2g means the 3 orbital possessing equal energy, so these are called as triply degenerated orbitals, and Eg means doubly degenerated, doubly degenerated orbital. This is the second postulate. And in this case, the T2g level, in case of octahedral complex, T2g comes to lower energy and Eg comes to higher energy. In both T2g and Eg, electrons occupy based on Wundt's rule. That is, they are going to follow Wundt's rule while accommodating electron in these two splitted orbitals. And the last is the after splitting, one going to occupy lower energy and another is going to occupy higher energy. So the energy difference between the splitted energy levels of d orbital is called as crystal field stabilization energy. Dear student, so once again, the crystal field theory, the postulates are very simple. That is, in the crystal field theory, he considered that both ligands or metal ion act as a point charges. They are treated as dipoles, molecular dipoles, and there is a ionic interaction exists between central metal atom and ligand. That is, the interaction, the bonding between metal and ligand is purely ionic according to this theory. And while forming a coordination bond, ligand approaches the central metal atom. While approaching, so there is a repulsion. You know that in chemical bonding you studied that while bond formation, both attraction and repulsion is exist. When attraction is dominant over repulsion, bond formation takes place. In the same manner, here also both attraction and repulsion is exist. But here, due to repulsion, splitting of d orbital takes place. That is, they split into T2g and Eg level. After splitting, the splitted d orbital follow Wundt's rule. This is the third postulate. And fourth one is, so the energy difference between splitted d orbital, that is Eg and T2g orbital, it is called as crystal field stabilization energy. So these are the important postulates of crystal field theory. So now let us apply this theory to various coordination complexes like octahedral, tetrahedral and square planar complex. Before going to apply this theory, you must know d orbitals and their shape. Then only you can easily understand this theory. Dear students, in the entire chapter, we are going to discuss magnetic properties, colored complex, high spin and low spin complex, stability. In order to understand, we are going to read electronic configuration. But in this chapter, we are going to electronic configuration in terms of T2g and Eg. You must know what is the meaning of T2g and Eg d orbital. It's very simple. When we come to s orbital, so s can only s. It possesses only in s subshell has only one orbital, that is called as s. If we come to p, there are three orbitals, px, py, pz. If we come to d, it has 5 orbital. D shell has 5 orbital. So the 5 orbitals are dxy, dxz, dyz, dx square minus y square, dz square. That means, so here dxy means the lobes of the orbital are present between x and y plane. That's why it is called as dxy orbital. Here you look at the CC, this is x plane, xy, and here the lobes of d orbital present along xz plane. So this is xz plane, and in case of dyz, so these are present on dyz. Dear student, there are 5 d orbital. One common sense is there are 5 d orbital. All the d orbital cannot accommodate in a same plane. Okay, same plane means either x, y, z. So they are accommodated in a different plane in order to avoid repulsion. So that's why they are based on the distribution of this orbital in a various axes. There are 5 orbital. So these dxy, dxz and dyz orbital. So and these 3 orbital having equal energy. There are 3 orbital having equal energy. That's why these are called as T2g. That means triply degenerated orbital. That is the 3 orbital possessing equal energy. That's why this is called as T2g, triply degenerated. And when we come to this dx square minus y square, dz square. Here in case of dx square minus y square, the lobes lie on x and y axis. In case of dz square, there are 2 lobes which is present on z axis, and the shape lie on xy plane around 2 lobes. So this is the okay, shape of dz square. So based on the shape and location, so they are going to give the name. Totally there are 5d orbital. Here you must know eg and t2g configuration. Now let us see the crystal field splitting in octahedral complexes. You know octahedral geometry. So octahedral complexes, these are the complexes in which they possess 6 coordination bond, or they're containing 6 monodentate ligand, and these 6 monodentate ligand, okay, present in a octahedral manner. So this is called as octahedral shape, octahedral geometry. There are 6 monodentate ligand attached, or it contains 6 coordination bond. In case of octahedral complexes, the ligand, we know there are two types of ligand, Eg and T2G ligand. In case of octahedral complexes, what happens? The Eg orbital, that is the dx square and dz square orbital, are situated directly towards the point of approaching ligands. The d orbitals of metal ions are pointing or directed to the path of approaching ligand, that is they are nearer to the path of approaching ligand. So because of nearest distance, what happen? If among 5d orbital, the Eg orbital, that is dx square minus y square dz square orbital, are nearer to the path of approaching ligand. If they are nearer, what happen? Repulsion increases. If repulsion increases, so they are going to occupy higher energy. But the other set of orbitals, so dxy, dyz and dxz orbital, experience lower repulsion. Why? Because they are not nearer to the path of approaching ligand. They are present between the axes. But these Eg orbital, they lie along the axis. So because of that, so they are experience more repulsive force, and they are experience less repulsive force. And the repulsion of octahedral compounds yield two energy level. Due to repulsion, what happen? So they split into two energy level. One is Eg and T2G levels. So now let us see, dear students. So there are 5d orbitals. So imagine this is the ground state. This is the d orbital before approaching the ligand. So now we are going to understand formation of a coordination compound in octahedral complexes. So in octahedral complexes, all the 5 orbitals are in ground state before approaching the ligand. When ligand approaching, what happen? So they undergo excited state. So in the excited state also, all the 5 orbitals are degenerated. So when ligand comes nearer, at that moment they split into two set of orbital, that is they split into Eg or T2G orbitals and Eg orbital. You just look at here, actually this is the energy curve. This is the energy versus reaction coordinate. So after splitting, see the energy level before it is in ground state, excited state, and in the excited state they split into two energy level. In the higher energy level, Eg is going to occupy higher energy and T2G is going to occupy lower energy. Why? Because Eg orbitals of central metal ion are directed to the path of approaching ligand, but T2G are present between the axis. They are not nearer to the ligand. As a result, they are going to experience less repulsion and they are going to occupy less energy. And dear students, the energy difference between, after this is called as crystal field splitting. When ligand approaches the metal ion, due to repulsion, the d orbital split into T2G and Eg orbital. This splitting is called as crystal field splitting. The energy difference between T2G and Eg is called as crystal field stabilization energy. This crystal field stabilization energy is represented as delta naught. So if the electron enter into T2G, their energy is 2.2 divided by 5 delta naught. If the energy enter into Eg, their energy is plus 3 by 5 delta naught. Why? Because if electron enter into Eg, they are going to destabilize the complex. If the electron enter into T2G, they are going to stabilize the complex. So this is how splitting takes place in case of octahedral complexes.